Hello everyone and a very warm welcome also in behalf of my co-authors to this presentation. Today we will talk about the integration of magnetic susceptibility and colorimetric parameters for loess-paleosol sequence from northern Serbia. You can see on the left side of this slide an overview map, like indicated with the red arrow of the region where we focus today on. It's the northern part of Serbia, and you can see on the map the major distributions of loess in this region. On the right side, you can see a photo of the Zeeden loess-paleosol sequence, and these brown stripes are paleosols which witnessed interglacial conditions, so warm and humid conditions. We used magnetic susceptibility and its frequency dependence as an indicator for the strength of pathogenesis. The frequency dependence is the absolute difference of high and low field magnetic susceptibility measurements. These measurements we performed on all 480 samples of the section, and you will see later where we introduce the H model that we are assuming that this loess-paleosol sequence covers the last 430,000 years. Additionally, we performed on 70 selected samples hysteresis analysis with aid of a vibrating sample magnetometer. In addition, we performed on all samples colorimetric investigations with a spectrophotometer to collect data of the luminance, the redness, and the blueness. And we also investigated the diffuse reflectance spectra in 10 nanometer intervals, which give us an estimation of qualitative contents of hematite and goethite. And afterwards, we created the hematite-goethite ratio. Here you can see a stratigraphical overview of selected magnetic and colorimetric parameters. You can see the former introduced paleosols, which show high values in susceptibility and its frequency dependence. The luminance, for example, is reduced. Note the inverted scale. And the redness is also increased. Furthermore, you can see two tephra layers, which are indicated in red, one in the L2 loess package and one in the means of the S4 paleosol complex. Later on, we will look a little bit on wavelet analysis. What you can see on this graph is that the part below the S3 paleosol complex is indicated by radial position due to the luminance, which is very high in its fluctuations. Carbonate concretions below S1, S2, and S3 are indicated in the left column by grayish-whitish dots. Here you can see that the Zeeden loess-paleosol sequence follows the general pattern of so-called magnetic enhancement, which means that you have, with an increase of the low frequency susceptibility, you have a simultaneous increase of its absolute frequency dependence, and the frequency dependence is an indicator for the strength of the pathogenesis because it tracks superparamagnetic particles close to the border of the stable single domain grain size, and we know that these particles are especially formed under pathogenesis, so under warm and humid conditions. Now we integrate magnetic susceptibility measurements, to be more precise, the frequency dependence with colorimetric parameters. I selected in this graph, on this slide, 4 colorimetric parameters, which I plotted against the frequency dependence. What you can see in all 4 subplots that loess units, which are indicated in bluish colors, are differentiable from paleosol samples. You also can see that the variation of the colorimetric parameters are very much increased in paleosol units. Now we come to the age model. What you can see here in the upper graph is the frequency dependence of magnetic susceptibility shown on the depth scale. And based on a correlative approach to the Lysakian Ramo stack and the ambient ice model, we were able to convert depth from the samples into age of the samples. And the result is the penultimate graph, so the frequency dependence on an age scale. And from that we can derive mass accumulation rates, which are obviously much higher in the glacials than in the interglacials. And this pattern follows the general scheme of the Eurasian Loess Belt, that we have increased mass input or dust accumulation during the glacials and reduced in the interglacials. What you can see now here is a test for the orbital parameters. So we performed on two selected values, the frequency dependence on the top and the hematite-goethite ratio on the base, a wavelet analysis. And you can see that there are slight differences in these parameters. For example, in these black dashed lines, they represent the eccentricity, obliquity, and precession. And especially in the precession and in the obliquity, we can see that the hematite-goethite ratio is a little bit more sensitive for these orbital parameters. Now we do a little outlook. So what I did is I created different age models based on different parameters. The result are 4 age models, 2 of them with the frequency dependence, where I once not included the tephra layers, and afterwards I included them as additional tie points. I also created an age model for the redness and for the hematite-goethite ratio. The result is now 4 different conversions of depth information to time-related information. On the upper 2 graphs, you can see the age model 1 and age model 2, one with the frequency dependence of magnetic susceptibility without the tephras, and on the right side including the tephras as 2 more tie points. On the lower 2 graphs, you can see the age model 3 based on the correlation of the redness to the Imbrian-Imbri stack and to the Lysakian-Ramo stack. And on the right side, you can see the same, but based on the parameter of the hematite-goethite ratio. Now it's interesting, what are the differences in these different age models for the ages resulting for the samples of the Zeeman loess-paleosol sequence. You can see here on the left side a comparison of the included 2 tephra layers frequency dependence age model and the redness based age model. And on the right side, you can see the same comparison of the frequency dependence, including the 2 tephra layers and the hematite-goethite ratio age model. And what is very important is here framed by this red box. On the very base, you can see the error estimated for the last 1 million years of the Lysakian-Ramo stack, which is around 4,000 years. But what you can also see is that we have, especially on the onset of the S3 and on the in around 100,000 years, we have differences yielding to 15 to 25,000 years. For the hematite-goethite ratio on the right side, we can see that we have there a big difference yielding to 30,000 years, but on the demise of the S3 pedocomplex, and as well in around 100,000 years we have the same peak of ages differences like in the left side of comparison from the both age models. So what we can say now is that all investigated parameters show clearly an eccentricity cyclicity. For all age models, the frequency dependence reflects obliquity, but the best 41,000 year intensity matched with power appears in age model 2. The frequency dependence in age model 2 reflects a quasi-continuous cyclicity over the last 350,000 years. Remember, the lower part of the profile we didn't analyze further because of the suggested redeposition. The redness reflects a strong match of power and a 41,000 year cyclicity in all three age models. The precession is not continuously expressed by the frequency dependence in all age models, and the precession is expressed better by all redness values in all age models. Then I played a little bit around, so I used different parameters creating the age model and looking at parameters displayed on this age model for the sensitivity of the orbital parameters. And we can see on the top left side that, for example, there I used a frequency dependence based age model and looked on the sensitivity of the redness. On the right side, you can see a redness based age model where we investigated the frequency dependence. And on the bottom part, we can see that we have a hematite-goethite ratio based age model where we investigated the redness as well. And you can see that we have, for example, the top right wavelet and the lower wavelet on the base, that we have there really massively changes in sensitivity of these parameters because they are more detectable for orbital parameters than other parameters. Now, to sum up, we compare the different depth age models. So what you can see on the right is on the abscissa the age and on the ordinate the depth, also with the two tephra layers indicated. And all four age models are in general agreement, and differences as I showed you before are the largest in the paleosol intervals. And we assume that these differences may be explained with different sensitivities of magnetic and colorimetric parameters for the climate variations. And we conclude by that A star, so the redness and the hematite-goethite ratio, are more sensitive than the frequency dependence to warm and moist conditions. Why? They are reflecting differences in onset and demise of paleosol intervals. To sum up and to take home, at the Zeeden loess-paleosol sequence, the combination of magnetic and colorimetric parameters traces eccentricity and obliquity for the last 350,000 years in the Zeeden loess-paleosol sequence. When we consider also the lower part of the profile, which is probably redeposited, we can assume a 430,000 year record. Differences in the age models, based on either magnetic or colorimetric parameters, reflect different sensitivities for the past climatic changes. And these different sensitivities for climate changes lead to different ages for the sample, which are higher than the uncertainty from the master stacks, Lisicki and Waymo, for example. This I showed you by the comparison of the different age models. The construction of an age model based on magnetic or colorimetric parameters shows that the simple wiggle matching approach of solarly susceptibility variations versus, for example, the Lisicki and Waymo stack or the Imber ice model leads to higher uncertainties. And this is the reason why we recommend to integrate magnetic and colorimetric signals. Thank you very much for your attention.